What's up, you guys? It's Peter here, and today I want to cover another one of these useful tools for your visual effects toolbox. It is going to be the SDF, or the signed distance field. So we're going to cover a little bit on how it works, and then also some examples on how to use them into Houdini and make them do and perform kind of tasks that are common to do for visual effects. So let's dive inside and have a closer look in Houdini how it all works. So first, let me shrink this down a little bit, and then we can dive into it. Okay, so I have a little example over here that shows you the signed distance field. And on the one hand, we have the SDF value. We also have the gradient length over here. And I've made a little point, a little sphere that is going to animate through it. And as it enters into the active voxels, it is going to start sampling the SDF, which is a signed distance field, and basically display a variety of information that we can then use for our sims or for snapping or for any kind of operations we want to do. So let's explain how it works, and maybe it's easier to understand backwards how to understand it. So signed distance field. The first thing to understand is that it is a field. That means we are dealing with voxels and volumetric data. The second part of it is what is actually being stored in those voxels, and that is going to be the distance. Now the distance, what distance? The distance to the surface. So I have over here this isocontour represents a slice of the pig's head, and you can kind of sort of see that we are measuring the distance, right, in red, the SDF value. We are measuring the distance to that surface. Now what happens when we are outside, right, of that zone, of that active region, is that this value goes to wherever the closest one is. So this, even though you can kind of sort of see, right, this is animating and moving, this distance should be updating, but it isn't. So why not, right? Well, because we're dealing with a VDB, and a VDB has got an active region. It can have what is called an exterior and also an interior band. And we'll talk about that in a moment. But the point being is, as soon as my point goes inside of this active region, the outside band currently, then we can kind of see it will correctly start sampling the values. Now, the second part of it, we'll talk about that later, is the gradient. Now, we'll talk about what a gradient is, and you can kind of sort of see this big blue vector, right, is a gradient. Now, let's keep going. We already covered field, it's a volume. We already covered distance, that means it is the distance to that surface. Lastly, we have signed, right? So why would it be signed? Ever heard of a signed distance, a negative distance? Well, no, not really. But by convention, it is agreed upon that any value that is on the inside of the geometry, it has a negative value. So it's got a negative sign in front of it. So I've kind of visualized that here with all the little plus signs on the outside, the negative signs on the inside. And if you look closely, we can zoom in a little bit, right? I've made over here a region, right, where the isocontour is 0. So by the way, isocontour, what does that mean, right? So iso means the same, and contour means a region. So a region where all the values are the same. In my case, here, this isocontour, this region where all the values are the same, right, where we are on the surface. And remember, SDF, the signed distance field, the distance to the surface. Well, if we are on the surface, then what is the distance to the surface? It will be 0. So therefore we start with a positive distance on the outside. We're going to be 0 when we're on the surface, and we will have a negative distance, more like a representation that we're inside of the surface, and that our distance value over here will go to negative. So as my value over here goes to the inside, we can see I am negative 0.264 units from that surface, right? Okay, so what I've built here is a little system that showcases the difference between the SDF value and the gradient length. Notice that the gradient length here is not necessarily normalized. It's got 0.924, and it's literally just a direction vector. Now, this is the direction vector from the current point to the closest point on the surface. That's quite useful to have access to when you're inside of your systems. So the other bit then is, well, what if I combine the gradient length together with that SDF value? That's going to be that little red vector over here that is pointing in the same direction as the gradient vector, but that has an SDF value. So the length over here of this little bit is 0.25. So if we kind of see that, you know, as we kind of get closer to this surface, we can kind of see that the length over here is going to get closer and closer to 0. Now we can't quite hit 0 because we are very close to that surface already. But as we kind of step through it, you know, it's kind of nicely sampling until eventually, boom, it is outside of my volume again. Let's talk a little bit about the volume next. We now know that, okay, we're dealing with a field. We have distance that we're sampling, and this is sign means we're inside or outside. Now we have the entire volume over here of our pig's head as well. So these are the bounds of the volume, and then these represent the active voxels. So that's the inside and outside banding. Currently, this is the outside banding, and the inside banding, you can't really see it because currently it is turned off. Let's dive inside of our SDF explanation and step through this. So I'm going to dive inside of this SDF explanation, and we have over here the pig's head. So we start off with the pig's head, and it's a polygonal surface, as you can kind of see. We're going to convert that into a volume. So if we look here, VDB from polygons, then we can kind of see this is the entire signed distance field represented as sort of a SDF as a voxel. So if you ever see this in the viewport, this is not polygonal geometry. If we hover over this, you can kind of see points, primitives 1, vertices 1, VDBs 1. And this is the resolution over here of your VDB. Notice also as we get closer, you can almost see the individual sort of, you know, visualization planes for representing that this is indeed a VDB object. It's not a polygon object. The last thing that is also quite useful to see is where that active region is. So if we turn on over here the hulls of your geometry, then it'll show you the active region of the active voxels. Now currently on the VDB we can see exterior band of 3, interior band of 3, and we can turn on the fill interior too. First, let's showcase what happens if we increase the exterior band. So if we go from 3 to say 10, it is going to expand over here this region, this area where the SDF is going to get computed, gets calculated, is going to be expanded. Next, we can also look at the interior. Now, in order to showcase the interior, I'm going to go to wireframe so we can see the interior data over here on the inside of our voxels of our SDF. If we turn on fill interior, you can kind of sort of see that that inside bit is now completely full. So if we turn it off again, there's my inside banding that's based off of 3 voxels. We can turn this into US world space as well, and we might later on make use of that when we are doing displacement of our volumes. And this might indicate our displacement amount or our displacement bounds. So let's turn this back to voxels, and let's go to this other one that I've already pre-configured. So if we go back to all the way at the bottom, my visualization over here, I can visualize this. Let's turn off the wireframe, and I'm going to go back to my camera over here. So let's showcase what happens if we turn off fill interior, right? So currently fill interior is turned on. So here, if we turn it off, you can clearly see the interior information is just gone. And again, my SDF value is not correctly being sampled because there is no data over here, right? So it'll try to grab whatever data is closest. So this is true for both the outside as well as the inside. Now, oftentimes, you know, the outside volume could be massive, right? There could be, you know, a lot of empty space over here. So the inside of a volume or the inside of an object might be a bit more contained, a bit more reasonable. Also, this could be good for liquid particles, sampling that kind of information. It could be good for little creatures crawling inside of another object or on top of an object. So there's a lot of use cases for this. So let me turn fill interior back on, and now my values are immediately computed again. Okay, so let's keep going, and let's see, as we kind of step through this, we can now sort of visualize how can we actually sample these values. So I have a sphere, I mentioned this before, I have a point. Now this is a primitive sphere. I like using primitive spheres because at the inside, at the center over here of that primitive sphere, there is indeed a single point that sits there. So that's mainly for visualization purposes and that I can easily move it around in the viewport. But I don't care about the primitive sphere, I care about that center point. So I could have just as well done this with an add operation and a point. Now here with the transform, I can kind of say, okay, I've got this animating, right, in the z-axis so that it moves over 100 frames from -2 to 2. I've also scaled it down so we can kind of just sort of see this little sphere move through my scene. This is going to move in relative to where my pig's head is. So we can kind of see, oops, So we can kind of see as it steps through, it is going to reference, all these values as we kind of go through it. How do we do this? Well, we can use an attribute vulp and we're going to sample the SDF. Now notice in the first input, I have my point. In my second input, I have my VDB. Right, so this over here is going to be my SDF, my surface, that I'm going to go and sample. So let's dive inside and have a closer look. Now, all of this we can basically ignore just for a moment. These are basically my rounding of my strings so that in my font subs it's not going to continue giving me all of this data. So we can kind of ignore that. But here, this is where we get to the good stuff. That is the volume sample from file. So we have two nodes here that are going to be quite useful. One is volume sample from file, and the other one will be volume gradient from file. So volume sample file is going to give me over here, using as inputs that point, that's my point's position, is going to sample in the volume. And where is that volume coming from? Well, we can either say a file name, so it could be a BGO on disk, and a BGO on disk might be useful if you are using Mantra or Karma for rendering. And then you can basically here also specify, whilst we're in subs, that the file name is going to come from up input 2, which is going to be our SDF, right? So my point then is going to spit that information out into an attribute. I'm calling that attribute magnitude. Now magnitude, it can be named anything. You can name this, SDF value if you want, but I like calling it magnitude because that allows me to sort of, visualize it in the viewport, or I can reuse it later on as well. It's not a reserved attribute. Magnitude is not a reserved attribute by Houdini, it's just my naming. So the volume gradient then, notice the outputs, the volume sample file is sort of this, I suppose a bit darker green. That means it's a float, it's a single value. Whereas volume gradient is going to be a bright green one. That means it's a vector. So even though volume sample exports a single float, which is the value of that distance, right, that sine distance, the volume gradient is going to compute a vector that is pointing from a low value to a high value. So remember, when we go back up, let's just visualize over here. I'm going to template this so we can kind of keep an eye on it as we kind of step through it, right? And kind of sort of see it. So that means that over here, this point, right, is going to create a vector that is going from a low value, a negative value, to a high value, a positive value. So let's go and see this. So we can visualize these values here in the spreadsheet. We can sort of showcase, I've got the gradient visualized, and we can also showcase the magnitude. Now these are the same values that I already had, right? So we have that negative 0.98, negative 0.98, and then my actual gradient over here is going to be pointing in a certain direction. Now this updates, right? So this is nicely sampled. And if we were to feed in 100 points, it will very quickly sample that volume without having to recompute all of those distance values, because that's ultimately the point of why you would want to use the SDFs. You want to sample the distance rather than compute the distance. In a later example, I'm going to show you the difference between, say, using array operation with a minimum distance and a volume sample with an SDF that is already pre-computed. So let's get back in here. So here I'm going to get rid of my my point basically, or rather my sphere, and we're left with just one single point, which has our gradient vector and my magnitude attribute. So next we can copy, and I'm going to copy a line. This line is aligned with the z-axis, it's of unit length, and I'm going to create a normal on this point that is pointing exactly over here. If we turn on the normal and we get a little closer, we can kind of see there's my point, and there it has a normal, and that normal is pointing in the direction of the SDF, right? So basically over here, that normal is pointing in the direction of the gradient of the SDF, I should say. Now a gradient doesn't need to be just on an SDF. A gradient can also work on a temperature field, and let's say, on the inside it's hot and on the outside it's cold. It's going to point from the outside to the inside. So temperature fields could be gradients, any kind of scalar value whereby you have a difference. So let's see, we bring in the gradient over here. Now notice when we said that gradient vector over here has a length of 1.0, but as we kind of keep going forward, right, we can kind of sort of see at some point, maybe here, for instance, gradient length is 0.36. So that means this gradient value is not yet normalized. So it's a good idea to normalize it, right? And then shove it into the normal. So that way we're dealing with a normalized gradient vector. On the other hand, I can also display over here the length and feed that into the p-scale. So this is going to be the length of that gradient vector and shove it into p-scale so that when I later on copy over here my little line segment on it, it is going to be of length. I mean, in this case, almost normalized, right? 0.999, but that is not a guarantee. So it's definitely a good idea that, you basically here 0.36, that you normalize your vector. Okay, and that basically after a polywire and a coloring, we can basically sort of see it's going to show up as this tiny little line segment, right? That is basically representing that gradient vector. On the other hand, I'm also going to, this is basically more useful. I'm going to make this little red vector, which is pointing in the same direction as the gradient, but it is going to be using the SDF value. So notice the gradient length 0.98, the SDF value negative 0.2. Now we're going to need to take into account that negative and positive value, because notice that over here, right, on the outside, if we look a little closer, you can kind of see that the gradient vector always points from a lower value to a higher value. So that means from a positive value to an even more positive value. Or on the inside, if we're over here on the inside, from a negative value to a positive value. Now notice what is happening with my other vector, my little red vector over here. My red vector is going to be pointing from the outside to this inside, and then over here from the inside to the outside. So it's basically pointing to the surface. So what I'm going to do is I'm going to make use of the gradient vector. We're going to normalize it, and then I'm going to negate it so that instead of pointing outwards, it's going to point inwards. Now this is going to be used in collaboration with that magnitude, right? That magnitude can go positive and can go negative. So we're almost doing a double negation when we're going to be on the inside, whereby even though we're going to negate our gradient vector, so it's pointing to the inside, because the value over here is negative, it is going to flip it around again. So it's like a double negation. So let's dive inside of our gradient, right, and see this in action. So here's my point. I've moved this one over slightly so that they're not sitting right on top of each other. And I'm going to say map gradient to n and also update our p-scale. So the gradient over here, same deal. We're going to normalize our gradient. And here's that negation that I was talking about. So as our vector is on the outside, right, it is basically going to showcase the normal to the inside. Let's just visualize that normal. There's that normal. Right, it's kind of a little hard to see, but it's basically sitting right over there. So that normal is pointing to the inside. Now the other part of it is going to be that magnitude that I'm going to feed into p-scale. Now remember what I was saying, magnitude is not a reserved attribute. P-scale is a reserved attribute that is going to get used by the copy operation. Okay, so let's keep going and let's have a look. So here my copy now, I'm going to copy that little line segment onto the geo. Polywire it, color it, so we've got now both of our line segments. Nice. So we've got the one that the gradient on the outside and the little inverse gradient, or the distance, direction, and the distance to the SDF displayed over here in red. Okay, let's see, what else do we have here? Well, these three font subs represent what I have in the viewport. They basically show me the sign distance field, so that's the sign distance field. They show me the SDF value, so that's literally just going to use a point string, a reference, the magnitude string that I've already computed. And then here, same thing for the other gradient length as well. Then I have my pig's head, right? So my pig's head outline. So notice when we start with this pig's head, I don't really want to display everything in full 3D space. Even though the SDF works in 3D space, I want to display this as sort of a slice in 2D, right? So it's a little bit easier to understand because it works in 3D, it works in 2D, it's the same deal. So let's make this representation of this contour. And the way I'm doing that is I'm grabbing my pig's head over here, right? And I'm going to match a grid to it. So we made a little grid. I'm going to use match size and make sure that scale to fit is turned on. And that is going to match this grid to the size. This is really useful for, creating outlines or creating slices or things like that. Then we can transform this up ever so slightly. So over here, I've scaled it by 1.1, and I've used an expression here, the centroid expression, together with input path of the incoming geometry. And then we have the dimensions in X, in Y, and in Z. Yeah. So these expressions are quite useful to have as a potential default, or potentially you can say, okay, save them as a new preset. And as you can kind of see, I already have one which is called centroid expressions as a preset. So it's useful just to have that. Would be nice if side effects added that as well, but nice to have as well. All right, so there's my centroids. Then we can do a Boolean operation and literally slice off the area where both my grid intersects with my pig's head. And that is going to be over here using the seam operation. So most of the times you're doing intersections or shatter, but I'm going to use the seam, which is going to give me that line that is basically intersecting between the plane and my pig's head. We can use that and visualize that. So polywire it and then change the color so that we can kind of see it in the viewport. Notice I've also used that later on to sort of scatter all of these little zeros onto it so that we can kind of see, okay, this value over here of the SDF is going to be 0. Okay, let's talk a little bit about the visualization of the SDF, of the active volumes. So we said before, right, that we have over here, this is my SDF, and notice my hulls are turned on right here, and they line up exactly with over here these little blocks. Now, what are these blocks, right? Well, so with these blocks, we can basically see with the visualize tree node, right, this can showcase, right, over here all the active voxels. Now you can say solid voxels, or by default it's a wireframe, right? So you can kind of sort of see these are all the voxels that are represented by these boxes. I just said solid boxes, it's fine. Now these are individual little boxes. So if you ever have to voxelize an object, it's very easy to do now with the sort of visualize tree operation if you want to. And then you can say with the assemble node, I'm going to pack this geometry and literally just go and turn each of these into its own tiny little box, into its tiny packed primitive. So that means if you look inside, we have all of these points and all of these individual boxes. I'm going to do a bounding operation, select just the middle section over here. You can say, okay, scale the bounding box down by negative whatever, make sure it has a minimum size, offset it just in the positive direction, so it's kind of slightly offset over here. We're moving it a little bit, and then using a group operation, I can say group inside, grab the points, enable the bounding box, enable the bounding objects. Now these points really represent packed primitives, right? So this is really going to select all of these little cubes, because we're dealing now after the assemble. I turned on create packed geometry, so we're dealing here with 1,700 packed objects. So the ones that I've got selected over here were 170, so great. Blast everything except for that little region. So now we're left with basically our voxel representation of these points. Cool. Next, I want to sort of indicate whether they're positive or negative. So we can use all of these boxes, and on the one hand, I'm already visualizing them. So that's going to be visualized over here. Basically unpack all of these little boxes, right? You can fuse them together, clean them up so there's no overlaps, and then turn them into a polywire. So now this is actually tiny little polywire geometry. Great. Next, this is part of the visualization, but we basically want to say, okay, go and sample the SDF, right? So this is what I was saying. Instead of sampling one point, I'm going to use all of these centers of these little boxes to sample all the values. So I can say attribute vob sample the SDF in the second input, right over here. This, if we follow this, is my same SDF again that is coming from my VDB from polygons. Okay, sample the SDF, same deal, right? So literally just volume sample, shove it into the magnitude, volume gradient. We don't actually need this, but we are after the magnitude. And so what can I say? Well, we can split them now using that gradient, right? So, or using that magnitude. If my magnitude value is positive, I want to copy some plus signs onto it. If my magnitude is negative, I'm going to copy some negative signs on it. So here with this split, we can kind of sort of see in the first input, right? This input here, it's going to be all the points on the outside, all the positive values. And then here on the second input, it's going to be all the negative values. So let's hide everything for a second. Here's all my points. I literally just made a plus sign and copied that to the points. So there's all my plus signs, right? And then we'll do the same thing for the negative signs over here with the fonts up and copy all this on the inside, just so that you can visualize them together. And then lastly, that outline of my pig's head over here, I resampled it so that we can kind of copy some zeros onto it. So I made over here just a 0, copy that on it. So we have all of the zeros visualizing as well. So if we merge all of that together, you can kind of see outside zone positive, inside zone negative, and then on the surface, it'll be 0, right? Okay, so that's so far for the visualization of all of this stuff, right? So hopefully you can kind of sort of start to see where this is useful. In the next section, I want to talk about the examples of what we can do with this, the application of it, right? So this is good for the theory, but in the next section, we're going to get into the examples of it. Now, I hope you enjoy this kind of videos. If you do, please like and subscribe, and see you in the next video. Thank you. Cheers.